Good morning. Today we're going to talk about section 6.5 in our textbook entitled Central Limit Theorem. And no pun intended, this really is a concept that's central to the study of statistics from this point in the semester on. I want to motivate the lecture with a bit of an informal example here. Let's say suppose we consider the entire set of all IQ scores of all time that have been collected, and I'm going to suppose these IQ scores are normally distributed, bell-shaped distribution, not too many high ones, not too many low ones, most are somewhere near the mean of 100, and a standard deviation of 15. I'm going to cite two different scenarios here, scenario A and scenario B, and I'm going to ask you which one of these answers is going to be greater than the other, A or B. I'll say randomly select one IQ score. And then I'll ask, find the probability that this IQ score is greater than 115. I'll use X to represent that variable IQ score. All right, in the next scenario, scenario B, I'll take a sample of size 30. Little n represents sample size, of course. And I'll let X bar represent the mean of that group of 30, that sample of 30. And I'll ask this then, what's the probability that that sample mean is greater than 115? The same limit is given in part A. Well, stare at this for a while with me and tell me what you think. What's the probability that a randomly selected, that one score is greater than 115, or that a sample mean from a sample of size 30 is greater than 115? All right, I'm going to claim A is greater. Let me write this down. Which is greater, scenario A or B? And I claim A is greater. All right? And it's easy to see why if you think about it right. Here we're only talking about one score, and greater than 115 is certainly significantly above the mean of 100. So I claim it's easier for one value to be in an extreme range as compared to a sample from a group of 30 yielding a mean. All right, let me write that down a little more formally. I'll say A is greater I'll say it's more likely for a single value or a single IQ score to be in extreme or even higher ranges than a mean of 30 scores. I think we can all buy into that. It's easier for a single score to be a fluke value than a mean from a group of 30. And the reason why is easy to see. By taking the sample mean and by taking the mean of a sample of size 30, you are really softening the effect of extreme values. I'll call it outliers. And it's more difficult for a mean from a sample to achieve extreme values in any given range. Okay? Alright, so there's our scenario for this motivation. Alright, Same scenario. Write this down. Same scenario. Again, you've got a bunch of IQ scores that are normally distributed with a mean of 100 and a standard deviation of 15. I'll say A. I'll say fine. Again, we'll randomly select one, similar to the first motivating example, and in part B, we're going to randomly select 30. And compute the mean. In part A, I want the probability that the randomly selected IQ score is between 100 and 115. And in part B, I want the probability that this sample mean is between the same two limits. So again, I'm going to ask, which is greater? A or B? Alright, if you stare at this long enough, I hope with that first motivating example, we can also grind out the answer to this one. Well, here, consider between 100 and 115, that's an interval that includes the mean, does it not? And I think you'll agree with me that B is going to be the greater answer. And for much the same reason we gave in the first scenario we talked about today, a sample mean from a group of 30, or any size, is more likely to be near the population mean value of 100. And again, the process of taking the sample mean reduces the effect of outliers, hence making it more difficult, if you will, for a sample mean to achieve high values seen in extreme ranges. Alright, what I've really done here is sketched out an informal definition of the central limit theorem. I want to be a little more formal about it here. What I'm going to do is consider a huge population of some values of some characteristic of interest, and every dot here, every mark, represents some numerical measurement of some characteristic of interest. And what I can do is actually plot the distribution of all these x values, perhaps millions of them. And I'm going to assume that these x values plot out a normal distribution. Let me draw it here. And I'll say this population of normal x values has some mean mu, and of course our bell-shaped curve will peak at the mean. Alright, what I'm going to consider now is from the same population, I'm going to take, instead of single x values, I'm going to take groups of x values and compute a sample mean. And then throw them back. Do it again. Take another sample. Compute the mean. Throw them back. Take another sample. Again, these samples may or may not overlap. The idea here is we'll get a long list of not x values, but sample mean values. And if I was to plot those sample mean values on top of my original distribution, I'll get a distribution that looks like this, a much narrower bell. So again, the yellow curve is the distribution of X scores, individual X scores. The red curve is the distribution of X bar values, sample mean values. And of course we can see that the process of taking a sample and computing a mean reduces the possibility of extreme values, doesn't eliminate them, but certainly you can see less of a spread. Less spread in the plot of X bar values, sample mean values. Okay? Less spread means less standard deviation. Lower, I'll write it like this, lower standard deviation. Remember, standard deviation measures spread. Alright, so I think we're ready to state the central limit theorem in words. We've given you a motivating kind of example. I've kind of stated it informally. Let's try to write it down, nail it down in a little more formality. The central limit theorem says this. The distribution of sample mean values is normal. Right? With the mean of the sample means, now don't panic, all this symbol means is it's the mean of all these X bar values. The mean of the sample means is equal to the population mean. All that means is these two bells peak at the same place. One's narrower than the other, that's all. And the standard deviation of the sample means, I'll use the symbol sigma sub X bar. SD of the sample means is your original population SD divided by this square root of the sample size. Now, I think you can see here, if I take sigma and my original SD and divide it by a quantity called the square root of n, I'm going to get a smaller SD than what I started with. Smaller SD, less spread. Less spread, narrower bell. Okay? I'll write that down again. Sigma over the square root of n. Alright. Let's do an example here. I want to refer, though, a lot of the homework problems refer to the, what they call the measured overhead reaches of adult females. Right? I'm going to let X represent a measurement of all the overhead reaches of all the adult females of all time, and I'm going to claim, or actually our textbook claims, that these overhead reaches of adult females follow a normal distribution with a mean of 205.5 inches and a standard deviation of 8.6 inches. Alright, much like we did in the motivating example, we're going to consider scenario A and B. And in scenario A, we're going to randomly select one. And in scenario B, we're going to randomly select a group. Let's say 49. In scenario A here, I wanted the probability that a randomly selected overhead reach of an adult female is less than 210. Well, of course, I'll grind this out with techniques I used in section 6.2. This is really the probability that X is between negative infinity and 210. As you may recall from section 6.2, we'll use our normal CDF operator, and I'll use minus 9999999 as an approximation of negative infinity. My right bound here will be 210. The mean and the standard deviation were of course given is 205.5, and the standard deviation here was 8.6. So if I punch this out on my calculator, I'll get a probability of 0.7. The probability that a randomly selected adult female has a overhead reach less than 210 inches is 0.7. And what I've really done graphically is considered this normal distribution of overhead reach values. The mean was 205.5. Right. We were asked to consider 210 as a right bound here, so 210 would give me this much area under that non-standard normal distribution curve, and hence this area is the probability I seek. Alright, nothing new there. That we did that in section 6.2. What's changed here is part B. From this sample of size 49, I want the probability that this sample mean is less than 210. Now we got to be a little bit careful here. X bar, by the central limit theorem, follows a normal distribution, right, with a narrower bell than seen in the original distribution. Right? The mean of the sample means is the population mean, and that is given to us as 205.5. The standard deviation of the sample means is going to be our original SD divided by the square root of the sample size, and here that's 8.6 divided by the square root of 49. So if I ask what's the probability that X bar is less than 210, well, I can write this out using my normal CDF command. Let me make sure I got some room here. Normal CDF. Again, I want to put a left bound. Well, less than 210 goes all the way down to negative infinity. So again, I'll use negative 999,999 as our author's approximation for it, negative infinity. The right bound is going to be 210. The mean of the sample means is 205.5. Now what's changed here from part A is the standard deviation. It's 8.6 divided by the square root of 49. Now, of course, the square root of 49 is 7. We won't always be so fortunate with perfect squares under that root sign. So I'm going to enter it in my calculator just like this. And I punch this out, and I get 0.9998. Alright, this tells me the probability that a mean from a sample of 49 is less than 210 is, well, essentially a certain event. Notice, the probability we got in part A was 0.7. The probability we got in part B, well, essentially a certain event. So certainly probabilities change quite a bit, or can change quite a bit, when you're investigating sample means from samples of size n. I want to do an example from the book now. Get a fresh layer here. I want to look at number 16 on page 294. They talk about a large group of M&Ms. Let me read this. Number 16. M&M plain candies have a mean weight of 0.8565 grams and a standard deviation of 0.0518 grams. Let me write that down. M&Ms, I'll say the weights of all these M&Ms have a mean. I'm going to assume that it's a normal distribution first of all. The mean of this distribution is 0.8565 grams, and the standard deviation is 0.0518 grams. Okay? Alright, now, the author goes on. It was essentially scenario A and scenario B again. Alright, much like the past four examples, we've got scenario A, scenario B. In scenario A, we're going to randomly select one M&M. And then we want to find the probability that it weighs more than 0.8535. So that's the probability that X is greater than 0.8535 in grams. Alright, we know x is normal. We know the mean and standard deviation, so we can grind out this probability just like in section 6.2 using my normal CDF command. Well, my left bound is going to be 0.8535. My right bound is going to be, well, in theory, infinity, and I'll use 999,999 as our approximation for infinity. The mean is 0.8565, and the standard deviation is 0.0518. All right, I punch this out on my calculator. Make sure I got all these numbers right. Looks good. I get a probability of a 0.523. Now what I have done really is considered my individual M&Ms, or the distribution of my individual M&Ms. I wanted the probability that x is greater than 0.8535. Now 0.8535 is a little bit below the mean value of 0.8565. So if I was to sketch this out, I really want the area under this non-standard normal curve to the right of 0.8535. Alright, and of course we make the tie-in between area under a normal distribution and probability. Alright, so this area is the probability I seek, and it's 0.523, we'll call it. Alright, now let's consider part B in this problem. Let me go to a different color here. We're considering a sample of 465 M&Ms. Alright, the book asks us, if 465 M&M plain candies are randomly selected, find the probability that their mean weight is at least 0.8535. Alright, so here I want not the probability that x, but the probability that x bar is greater than the same limit, 0.8535. Alright, the central limit theorem tells us sample means are normally distributed with a mean that follows the original population mean, which here was given to us as 0.8565. The standard deviation of the sample means is your original SD divided by the square root of the sample size. And here that's 0.0518, and the sample size is 465, so the denominator is going to be the square root of 465. Alright, so I know the distribution of x bar is normal, so I can use my normal CDF command now to grind out the probability I seek. Let me be sure I got enough room here, because it's going to be a long command. Normal CDF. I consider the limit here. The left bound is going to be 0.8535, will it not? The right bound, well, theoretically, x bar goes off to positive infinity. So I'll use 999,999 as an approximation for positive infinity. The population mean of the sample means equals the population mean originally given. What's going to change here is your standard deviation, 0.0518 divided by the square root of 465. Notice in this command in part A, this entry here was 0.0518. What's happened here in part B, all that's changed really is you've got a different standard deviation, less of a standard deviation, right? If I punch this out on my calculator, again, let me make sure I got it, 0.8535, 999,999, 0.8565, and then 0.0518 divided by 465. I would type it in just like I see it here, let the calculator do the work, and I get a probability of 0.8941. Alright? So again, if we consider the answer to part A, on this particular problem, the probability in part B was quite significantly higher. Alright, central limit theorem in action. Again, let's do one more question. I believe this one's a homework problem. Yes, it is. It's redesign of ejection seats, number 19 on page 295. Much like the 4 or 5 examples we've already done today, let me read through the problem. When women were allowed to become pilots of fighter jets, engineers needed to redesign the ejection seats because they had been originally designed for men only. Okay? The ejection seats were designed for men weighing between 140 and 211 pounds. Alright. Weights of women are now normally distributed with a mean of 165 and a standard deviation of 45.6 pounds. Let me write that down. Weights of women. I'm going to let X be a variable that represents all the weights of all adult women of all time. And the author claims these weights are normally distributed with a mean of 165 and a standard deviation of 45.6 in pounds, right? Alright, so they want us to consider again part A and part B, following the template as before. Again, we're going to randomly select one in part A. We want, well, it says, the author says, find the probability that one randomly selected woman is between 140 and 211 in pounds. Alright. And again, we're only talking about one woman here, so I can use techniques in section 6.2, in particular our normal CDF command. Well, our interval of interest has 140 on the left bound, 211 on the right bound, and the given mean and standard deviation. And I can punch this out with my TI-83, and I get 0.5517. So all this is really, it's a probability that I can interpret graphically as shown here. Women's weights are normally distributed with a mean of 165. And we want the probability that a randomly selected woman is between 140 and 211. So what the calculator has done for us is computed the area under this probability density function between the limits of interest, namely 140 and 211. So this is the area we seek, and that area is this probability, okay, 0.5517. And if you look at the curve, that looks about right. Now part B. If 36 women are randomly selected, find the probability that their mean weight is between the same limits. So essentially I write the same limits, but instead of X I write an X bar here because I'm talking about a sample mean being between these two limits. Central limit theorem says sample means are always a normal distribution. The mean of the sample means is the same as the original population mean. The standard deviation changes, however. You get your original SD reduced by a factor of 1 over the square root of n, or your SD divided by root n. So I'll write my SD 45.6 divided by the square root of 36. All right, let me see if I can get this in properly using my normal CDF operator. The lower bound here is 140. The upper bound here is 211. The mean of the sample means is 165. The standard deviation of the sample means, I'm going to write it just like I see it here. Let the calculator do the work. If you want to do intermediate calculations to get a standard deviation before you punch it in, that's fine. Try not to round off too much. If I punch this out, I get a 0.9995. Alright, so in part A, we got a probability of about a half plus some change of being between these two limits. But notice in part B, this has gone from about a half probability to almost a certain event of being between these two limits when taking a sample mean from a sample of size 36. Alright, so that ends today's micro lecture or video lecture on section 6.5, central limit theorem.